All right, so it's good to be here. My first presentation in Florida. I have a lot to share today. Hopefully they'll be able to make the slides available to you. There's nothing proprietary about any of this kind of stuff. So my charge is to talk about innovative fertilizers, which there's only really one or two I'm going to mention today, but other things that you might consider to improve end-use efficiency. So as you've seen, I think from several presentations already, the movement, it seems, is to maybe go to a more spoon-fed approach with your nitrogen. I saw some wide drops and things, and so ultimately that's what we found to be useful up here in the Northland and in different areas around the country where there's irrigation or a lot of rain or something like that. Spoon feed the crop through the season. Directed with tissue analysis. So I have a feeling that's probably where you're going to go someday, but that's not what I'm going to talk about today. In addition to the nitrogen fertilizer, I'm going to address urease inhibitors, nitrification inhibitors, and also a little bit on the effectiveness to date of those commercial nitrogen fixing bacteria that you can buy. So the problem with urea when you apply it to the surface or near the surface within a couple inches of the surface is that it's transformed by urease enzyme in the soil to free ammonia and CO2. And if the pH is above 7, it drives the reaction toward ammonia gas. If the pH is less than 7, it drives the ammonia toward NH4 and is harder for it to volatilize. But some is going to volatilize no matter what you do. So I don't know what you know about enzymes, but enzymes are a three-dimensional thing. They have a three-dimensional purpose, just like individual tools in the toolbox. And this is the shape of the urease enzyme. It has a nickel as its metal in it. It's the only reason why nickel is an essential nutrient. And it's made by plants and bacteria. Almost all plants and bacteria have this enzyme in it, and it's very resistant to decay. And so when the rest of the plant, the bacteria decays, the urease is one of the last things to go. And so it's in the soil, it's in all of our soils. And when it bumps up against a urea, it does what it used to do in the plant. This is my favorite study on urease inhibitors and other things. This is some work from Kentucky. A number of years ago in corn, they had a pre-plant rate of 50 pounds of N, and then they applied nitrogen on top of that. And then the yields of corn were on over there on the right. Your check is 117 with the 50 pounds only, and then with the added N is urea, 158. That looks like a win. But then you put the urease inhibitor on it. This is long-term no-till. The agritane, the NPPT, and you get another 43 bushels. And Super U has NBPT in it also with DCD, but agritane, the NBPT, is the star of this one. And you get about the same rate. So there's no denitrification. It was strictly the ammonia coming off the urea. UAN always takes a hit if it's broadcast, and you see this in the study also. And the agritane did help that also, about a 25% roughly. The nitrogen and UAN, as you know, is nitrate, and so that's subject to leaching and all kinds of nasty stuff. So the lesson number one is that you're putting your urea at the surface, putting on an NBPT urease inhibitor at the proper rate is something you need to consider. But then lesson number two is the very last one, ammonium nitrate. And we don't use ammonium nitrate anymore because crazy people blow up buildings. But in the research world, we use it once in a while. We have to document it and everything, Homeland Security. But when they used ammonium nitrate in the study, which has no volatility at all, then they increased the yields over the NBPT treated urea by 38 bushels an acre, which means that even with the NBPT, that there was a period of time afterward where there was some ammonia volatilization. And so if you can get the urea 2-inch, more than 2 inches underneath the soil, or use anhydrous ammonia, something that's going to be at depth, then you may be ahead. So anyway, those are the two lessons with that. So I mentioned a couple times you need to get the urea a couple inches over the soil, and it used to be that when I would talk to people over the phone, and they'd say, well, I put urea over the top. Should I incorporate a little bit with a vertical tillage or something? And I say, yeah, as long as you get the urea covered, you're okay. And then somebody actually did the work, because it's not a good thing to assume. So this article appeared almost 10 years ago in the Journal of Environmental Quality, which is a highly rated journal. This first period here is about a week. And so after the first week, if you just left it on the surface and didn't do anything to it, the losses were 2%. And if you incorporated an inch, you lost almost 9 times that. And you think, well, how is that possible? And I think it's possible because when you're putting urea on the surface, it's only in the intimate contact with the certain percentage of urease possible. But then when you cover it with soil, you're increasing the amount of urease per pellet, and so you increase the loss. So that incorporation isn't helping. So I tell people now, I said, well, should I use a vertical tillage to just cover it with soil? And I say, use NBPT and leave it the heck alone. So how does urease work? So it's a three-dimensional entity, as I said, and it's not just a blob that just kind of rolls around like an amoeba. It actually has a very big structure in it. And in the middle, if you turn it just the right way, and you can do this yourself if you go into PubChem, which is it's a public site, and put in urease, you can get the glob, and then you can rotate it around three-dimensionally. You can see this triangle hole. Why is that important? Because this is urea. NH2, NH2, CO, right into that triangle. And that's how it works. Bumps into the urea, draws it into the triangle. It changes shape. It cracks the urea into ammonia and CO2 in the presence of water, and there you go. So that's and the inhibitor is made the same way. So it's not urea. That's that long name there at the top. But it has a triangle shape. And so this inhibitor, the MBPT or NPPTs, I'll show you, but it fits right into that triangle. But instead of being transformed by the urease, it just sits there. So it renders the urease inert for as long as that tail stays around. At some point, there's some kind of organism that breaks that tail apart, or maybe it's hydrolysis. But the electrostatic charge changes and the inhibitor falls away. But in your area, I think you should expect at least a week of 100% urease inhibition. And then hopefully by that time you get a rain or an irrigation or something like that, and then you're good to go. So there's two different chemistries that work the same way. MBPT is the old Agritane, and now there's plenty of private label MBPTs. And PPT, all the difference between the top MBPT and PPT is the limus has a longer tail, and that's a product marketed by BASF, but as far as I know, they don't market it very much. If you're going to use a private label MBPT, you need to look at the percent MBPT on the label. If you used Agritane Ultra, which is a Coke product, 3 quart per acre or 3 quart per ton of urea, the density is 8.9 pounds per ton. If you do the math, that's about 1.8 pounds of MPPT per ton. So as long as you use that rate of active ingredient per ton of urea, it doesn't matter what you used. We've used Tech MBPT in our studies, Agritane MBPT, and it's the same. And ask Lakesh about his joyful time doing all this work with the sledgehammer, and he'll be glad to share that great experience with you. All right, so that brings us to nitrification. As I said, almost 100%, nearly 100% stopping urease activity with the MBPT. It's not the same with nitrification inhibitors. They slow the process, but they don't stop the process. So so this is a reaction, 2 different kinds of bacteria, multiple species within each one. It works when it's moist. It works when the temperature is 80 degrees or so, which is pretty much Florida. And then the pH is favored by pH above 7, slowed by pH less than 6. But it happens in all of our soils. All right. So why aren't you advancing? Go, go, go. Go, go, go. Here we go. Thank God. All right. So this is the original nitrification inhibitor, at least one of them, nitropyrin, and the structure really doesn't lend itself to explaining why in the world it works. It essentially kills the bacteria that do this. This is a study that I worked in. As I said, I'm very old. So this is a study in Illinois that I worked with. Joe Touchton was a dean, I think, down at Auburn, as I remember, until he retired here a few years ago. But I worked with him. So I wanted to show this to you, not because you're going to do things in the fall, but I want to call attention to this this chart here in the lower right, and that's what you would be using. So you'd be using maybe nitropyrin with ammonia, maybe in the spring of the year. The breakdown of ammonia in a warmer environment is relatively fast. Yes, it does something. This top line here, this top curve is with the nitropyrin, and the bottom curve is without. So certainly it keeps ammonia in ammonia form a lot longer. But you're dealing a lot with sandy soils down there too. And so I don't know, is there CEC now that your organic matter is almost nothing? Is it high enough in order to do anything? I don't know. Lakesh can tell you that. But if you do have CEC over 10 or so, then maybe this is important. NSERF has corrosive issues. Most of you in the fertilizer business are close to it, know that. Instinct is, and all of its siblings, made by the same company as NSERF, is micro encapsulated, and so that's good because it can stay on the surface and wait for an incorporation. But there's another reason why maybe it's not so good. This is some work by Jay Goose and his colleague down at Auburn that looked at different soils and the amount of residual ammonia after a period of time. What they found, this is the labeled rate right here, down here at about 1 part per million or so, and with the nitropyrin on urea, which you can't do commercially because it just mush pretty much. It's too much liquid, and that's the reason for the instinct. It is effective, more than half of it after about a 4-week incubation. But it needs to be what, at least a double rate, maybe more than that rate of the instinct in order to get anything similar to that. So, and DCD, and talk about that in a minute, and that's not even as good. So these things have some activity, but are they really wonderful? And should you just ignore the side dressing and just go with this? I think not. DCD was first developed as a fertilizer, but it was toxic to plants at high rates, and so they found that it was a nitrification inhibitor too. So this is the other chemistry. So we have nitropyrin, we have DCD. That's pretty much it. DCD is found in Agritane Plus. It's found in Super U. There's also some products that you can spray on the pellets, but I don't think they work real well because it needs to be, the rate that you need is about 1% of the total nitrogen in your mix has to be DCD. If it's lower than that, the activity greatly decreases. The best commercial product is about 1.2%. And that's the Super U. Which brings us to the specialty fertilizers. So the big specialty fertilizer, I think that's important and available is the polycoated urea with ESN from Agrium, with moisture and needs moisture. The urea moves out the side of the coating and into the soil, and it's slow. The best way I've seen in some of the research that's done north of you to use it is in kind of a blend, which Dave Mengel did up here in Kansas with about 50% just urea and 50% ESN. If it's really, really dry and you use all ESN, you're in big trouble because the urea is not going to come out. And then there's a product called Centuro. Yeah, I know almost nothing about it except this is this is what it looks like. Very, very limited research. Coke has been very tight to the vest about this kind of stuff. So I don't really know what to say about it. What about other products where there's a claim of nitrogen activity, but there's no mode of action and no convincing evidence they work on nitrogen ability at all? I think you need to buyer beware. Companies are letting tech reps go. They have a lot of development and then they're marketing, and then maybe they do research after it comes to market. So be extremely skeptical. Which brings us to the last thing I'm going to talk about, and that's the nitrogen fixing organisms in the commercially available. So over the last couple of years, I'm in a group of non-conventional additives and amendments with the North Central states, and these are the states that contributed: North Dakota, Minnesota, Illinois, Indiana, Missouri, Kansas, Michigan, Kentucky, Nebraska, and Ohio. And so we looked at Envita, we looked at Utrisha, which is a foliar stuff, and then the Pivot Bio materials, and then another company that I don't know a whole lot about from Minnesota. And I'm just going to focus here on the corn experiments because you don't really care about those other crops. There were 53 total of corn experiments throughout all those states, and 51 of those experiments found no benefit to yield over N rate alone when adding those products. There were 2 with benefits that resulted, if you did the math, the N rate benefits were 12 to 20 pounds N per acre, which is about, what, a third and a half about what the marketing tells you sometimes. So what do you to take about this? There's 100 companies working on these things right now, and so these are things you need to keep in mind. You need to understand that since 2008, the burden of research falls on the user. Companies are good at development, but the research is sparse, and sometimes results from university researchers may be controlled by restrictions from signed confidentiality agreements, which I refuse to do, but some people do. Growers need to be skeptical about new products. You need to try them on replicated strips on the farm. I want to refer you to Laura Thompson's article in 2022, Proceeds of the North Central Extension Experience, the Industry Soil Fertility Conference. She has a really nice paper, and it's accessible to anybody. This is an example, tells how to set up experiments. You apply the nitrogen on the go, harvest the corn with a yield monitor. We also have a publication about this that goes into a little bit greater depth. And you can pull this on the line. It doesn't cost you anything. So with that, I think I'm up against time because I covered a lot of things. These are my contact information if you want to get a hold of me in the future.